stuck like glue.
Alright, 7.3 is on combinations. It's another type of counting. It's very similar to what we did last time, permutations. This is called combinations. What's the difference? Well, with a combination, it's a selection from a group of objects in which order is not important. Okay, remember last time, permutations, we said the memory device was permutations, position. The position or the order of things matters. But with combinations, order doesn't matter. So an example of that would be like dealing cards. When you're playing cards, I don't know if you ever play cards, but when you play cards, it doesn't matter whether you get dealt the Queen of Spades as the first card or the fifth card. It's just one of the cards in your hand, right? Same with picking lottery numbers. If you pick the number 7 as one of your numbers and it shows up as the third number, there's never a case, I don't think, in lotteries where you're like, oh darn, my number came up, but it came up third and I want it to come up first. No, that's not how a lottery works. As long as your number comes up sometime, it's fine. Order does not matter. So to try to distinguish the difference here and to also figure out the formula for combinations, let's take a look at an example here. Let's say you're going to pick 3 things. Let's call them A, B, C out of 26 things. We must be talking about the alphabet, I guess, here, right? Out of 26 letters, we're picking 3, A, B, C. If order matters, in other words, we're talking about permutations, how many different possibilities are there? Well, there'd be A, B, C, A, C, B, B, A, C, B, C, A, C, A, B, and C, B, A. Okay? That's if it's or if order matters. If order doesn't matter, then what would it be? Well, it'd be ABC. I mean, you could write it in any one of those ways, but that's all. It's all the same. These are all the same as each other if order doesn't matter, right? If you're getting dealt cards and each card had a letter of the alphabet, whether you got dealt ABC or ACB or BAC or blah blah blah, it's all the same because order doesn't matter. Okay, so how many more options are there in the permutations than in the combinations? There's 6 times more. There's 1 here, there's 6 here, so there's 6 times more. Now why? Why six times more? Because the reason there's more here is you're allowed to rearrange these. How many times can you rearrange 3 things? Oh, we've done that a whole bunch of times. If we want to rearrange 3 things, that is equal to 3 factorial, or 6. So there's 6 times more because 3 factorial, or 6 ways to rearrange 3 things. If we wanted to know all the permutations, like how many permutations are there of picking 3 things out of the alphabet here and order mattered. If order mattered, we'd be looking for permutation of 26 items and you're taking 3 of them. And the answer, based on our formula last time, would be 26 factorial divided by 26 minus 3 factorial. For combinations, you can write it the same sort of way, except you don't put a P, you put a C. If we want to know the combinations, so in other words, again, we're going to pick 3 things out of this alphabet, but order doesn't matter this time. It would again be 26 factorial over 26 minus 3 factorial, but we have to add one little bit. Now, is there going to be more or less combinations? There's going to be less combinations. Why? Because all the different rearrangements here don't count. They're all the same. They all count as 1. So how many times less should there be? 6 times less, right? Or the way that will always work is it'll be 3 factorial times less. Okay, if that was confusing, it's not totally critical. I'm trying to give you a sense of why the formula is what I'm about to show you right here. If you're looking for the number of combinations of n different objects taken r at a time, and if order doesn't matter, then first of all, there's a couple ways you could write it. You could write it the way I already wrote it, and that's the way I usually write it. You could also write it like this, C and then n and r in brackets. You could also write it like this, a bracket with n and r. That's not a fraction. And either way you write it, or any of those ways you write it, the answer will be n factorial over n minus r factorial, which is exactly the same as permutation. But then you also have to add in r factorial. Why is that? Because that's all the different ways you could rearrange the objects you're picking out, and those ones don't count because rearrangements don't make any difference when order doesn't matter. Okay, so that's the formula right here. The way you say these things is you say n choose r. So up here, for example, in this question that we did up here, the way you would say this is 26 choose 3. So let's try a few questions. A group of 5 students is to be selected from a class of 35 students. How many different groups can be selected? So in all these questions, these are all combinations. Order doesn't matter, but you want to get used to the idea of being able to identify whether order doesn't matter or not. So this case, if you're picking 5 students, order doesn't matter, right? Because whether you pick them first or fifth, they're still part of the group. If I assigned jobs for those 5 people, if I said, you're going to pick 5 students, and the first one's going to be the president, the second one's the vice president, the third one's the treasurer, etc., etc., then it wouldn't be a combination, it'd be a permutation, because order would matter. Whoever picked first is going to be one thing, whoever picked second is going to be a different thing. So it can be very difficult to figure out whether it's a permutation or combination. In this case, it's a combination. So what we're looking for is 35, choose 5. We have 35 items, we want to choose 5 of them, and order doesn't matter. So how do we do that? We do 35 factorial over 5 factorial, that's our r value, times 35 minus 5 factorial. Okay, you could throw this all into your calculator, because your calculator, if it's scientific, should have a combinations button. Or of course you could simplify this and you'd end up having to go 35 times 34 times 33 times 31, cancel out the 30 factorials and still be left with 5 factorial on the bottom. It's a little bit of work, so I'm not going to do it, actually. I'll just write down what the answer is. Once I use my calculator, you get the answer 324,632. As I've said before, there's a lot of very large answers when you do these sorts of questions. Okay, now same sort of question. You got your 5 students to be selected. What if Lisa, Gwen, and Al are in the class, and we want to know how many groups include those 3 students? Well, if we include those 3 students in the group, so we have this group and we already have Lisa, Gwen, Al, and then there's only 2 more to choose from. How many students are there to choose from? Not 35 anymore, because these are 3 of the students. There's 32 students left, and we need to choose 2 more of them to fill this group. So you figure out what 32 choose 2 is. Again, you could make it 32 factorial over 2 factorial and 32 minus 2 factorial, or you could just pick up your calculator and plug it in and you'll get 496. I encourage you to try doing that in your calculator. Make sure you know how I'm doing this. How many of the groups do not include all 3 of these students? Oh boy, how are we going to do that? What should I start doing here? Well, believe it or not, we've already done all the work almost. If this is all the groups there are total, and this is all the groups that include all 3 of them, then how many groups don't include all 3 of them? Well, it'd be the total, take away the ones that do include all of them. So all you have to do is go 324,632, take away the 496 groups that include all 5 of them. Sorry about that. And if you do that, you'll get the answer 324,136. So be careful of that. Sometimes people have to do these subtraction steps like that. Okay, a few harder ones with cards. Cards are very common. I think all of them, yeah, these are all cards. So if you don't know about a standard deck of cards, a standard deck of cards has 52 total, and there's 4 different suits, right? The suits are what? We got spades, we've got clubs, we've got hearts, and we have diamonds. And thankfully, the way I've drawn it here, these ones are red, and these ones are black. Do we have a black here? This will probably ruin everything. Black, black, good. Now you can't even see them. Isn't that wonderful? Okay, in each one of the suits, there's 13 cards, right? Ace, 2, 3, 4, 5, 6, 7, 8, 9, 10. Jack, Queen, King, and we already got these down there. Okay. So how many different 5-card hands can be formed with only red cards? Well, first of all, how many cards are there that are red? Well, half of them are black, half of them are red. So there's 26 cards that are red, and we want to pick from those 26 cards a 5-card hand. So we want to choose 5 out of there. Okay, so you can pick up your calculator, or you can do it the long way if your calculator doesn't have the function. You would have to do 26 minus 5 factorial. You have to do that, and when you do that, you will get the answer 65,780. Now, how many different 5-card hands can be formed containing exactly 3 black cards? Well, if you're going to get 3 black cards, what exactly do you need to get? You need to get 3 black cards, and you also need to get 2 red cards. So we're going to have to figure out what's the how many outcomes are there for both of these, and then multiply them together. Okay, so to get 3 black cards, that means out of how many black cards are there total? 26. You have to choose 3 of them. And for red cards, there's also 26 of those, and you need to choose 2 of them. So you pick up your calculator and you figure out what 26 choose 3 is, and it's 2600. And you figure out what 26 choose 2 is, and it's 325. And then when you multiply together 2600 times 325, you get the final answer, which is 845,000. Okay, so that's how many 5-card hands can contain exactly 3 black cards. How about this? How many different 5-card hands can be formed containing at least 3 black cards? Well, at least 3 black cards could be a bunch of different situations. One could be 3 black cards and 2 red cards. That's what we just did. So we know what the probability. We know how many outcomes there are with that. There's 845,000 outcomes in that case. Another possibility would be 4 black and 1 red. And the final possibility would be 5 black, 5 black, and 0 red. Right? All those conditions have at least 3 black cards. So we still have to figure out these ones. Well, it's going to be very similar to what we did up here. 4 black, well, out of the 26 black cards, we want to choose 4, and then we have to multiply that by, in the reds, of the 26 red cards, we want to choose 1. So we got to figure that out. Let's do this at the same time. 5 black. Well, of the 26 black cards, we want to choose 5 times. You can do this if you want. Out of the 26 red cards, we want to choose 0. That's fine. You can do that. We'll talk about that in a second. Okay, 26 choose 4. Put it in your calculator. You're going to get 14,950 times 26 choose 1. You should know what that is. If you have 26 cards and you want to pick one of them, how many ways can you do that? 26. You can pick the first card, the second card, the third card, all the way up to 26. So that gives you 388,700. 26 choose 5 is 65,780. 26 cards, and you're going to choose 0 of them. How many ways you can do that? Believe it or not, that's not 0. You can choose 26. You can choose 0 out of 26 cards in one way, by doing nothing. So the final answer there is 65,780. Now, what are we going to do with all 3 of these answers? With this answer, and this answer. You're going to add them together because these are 3 different possibilities, and you add the 3 different possibilities together. You see why here you multiplied? In this question you multiplied, and here you're adding this final step? Because in this step you need both of these things to happen for the one instance. But in the final in this question here, you could have this instance take place, or this instance take place, or this instance take place. Okay? And you still had to multiply within each one of these instances, just like we did up there. Hopefully that makes sense to you. So to get your final answer, you're going to add together 845,000 plus 388,700 plus 65,780. And if you do that, you're going to get 1,299,480 hands that have at least 3 black cards. Okay, last one. How many different 5-card hands can be formed containing all cards of the same suit? Okay, well, let's just think of one of the suits. Let's think of diamonds. Okay, what's the probability of getting 5 cards all diamonds? Well, there's 13 diamonds, and we would need to choose 5 of them. How about hearts? What would it be? Well, it'd be 13 choose 5 as well. How about clubs? I think you're getting the point here. 13 choose 5. Spades? 13 choose 5. So in other words, what you need to do is do 13 choose 5 to see how many 5 cards hands there are with just one suit the same, and then you need to multiply it by 4 because there's 4 different possibilities. Or the other way you could do it is you could get this answer, this answer, this answer, this answer, add them all up, but they'll all be the same, so it's the same as multiplying by 4. Okay, 13 choose 5 is 1,287. You multiply it by 4, and you get 5,148. By the way, in poker, if any of you play or are interested in poker, this is called a flush. When you get all 5 cards that are the same, it's pretty rare. It's only 5,000 over 5,000 hands that this happens, and there's millions of hands possible in poker. Okay, that's the end of combinations. I hope this is making sense.
The